Welcome back, Math 10s, for our final lesson. It is on arithmetic sequences, which is just kind of a application or a different way of looking at what we've been doing with linear relations. They are linear relations. So let's dive into these things that create quite a nice pattern, and it's the most basic form of sequences. Later on, you'll do more advanced topics in other math classes with sequences and later things called series. So let's just dive into this introductory. A sequence is just an ordered list of objects or numbers, okay? And the elements or terms follow a rule to determine the next term in that sequence. All right, and we're going to look at these in very simple cases. An arithmetic sequence is an ordered list of terms in which the difference between consecutive terms, okay, so consecutive means one after another. Consecutive terms is constant. It's always the same, which rings a bell with linear relations. They have to be changing at a constant rate, consistency. This difference is called the common difference. And we saw this in different examples when we were plotting these. And it's usually donated by the variable d when we're talking about arithmetic sequences. And since these sequences are linear, the common difference is simply the rate of change, which is something we already know about. So let's take a look at um, some sequences, and it's just saying write the next three terms. In other words, find the pattern and what are these increasing by consistently. The constant rate here is plus 0.06, and next we get another plus 0.06. So being told that this is an arithmetic sequence, the next terms must also be plus 0.6. So we get 5.8, 6.4, and 7.0. Okay, so in this case, our D is equal to 0.6. Next, we look at how these things, this sequence is changing. It looks like it is decreased by 3 and decreased by another 3. So this is getting more and more negative. We're going to get -8, -11, and -14. So our D in this case, our common difference, is equal to -3. All right. Well, what if things that's pretty simple? That looks pretty elementary so far. Let's write an expression that will give you the value of the sixth term of an arithmetic sequence, 3, 8, 13. And then what's more challenging, we want to generalize it to find the 100th term. We want to find a fast way to get really big terms because generalization means we're going to have some type of formula or algorithm to determine that. So what we're first going to find is term number 6. And we're going to denote that this way. We're going to write T6. And so what that means is coming from here is this is saying this is the sixth term is what we're trying to figure out. Okay. And now we know the first term is 3. And then to get to the second term, looking at this pattern right here, we find the common difference. This is plus 5, plus 5. So we can see right away that our D is equal to 5. So we're going to take 3 and we're going to add 5. Okay. And so what we want to look at here is that right here we have, let's change colors. There we go. Okay, so right here, that's our first. All right. But then if we combine both of these, okay, 3 plus 5, that's going to give me 8, right? That's going to be my second term, or T2. And then we're just going to keep on going here. Let's keep adding 5. So if I add another 5, that's going to be my third, my fourth, my fifth, my sixth. Okay, so just to kind of make that show exactly how this is changing, every time I'm adding another 5, so if I take all 3 of those, that's my third. And then if I take all 5 of those, that's going to be my fourth. And then if I add another 5, that was my fifth term. And adding one last 5, that's my going to be my sixth. So now I have to add this whole thing up. But let's actually look at this in a different way. Normally, we don't repeatedly add. We're going to turn that into multiplication. So this would be 3, my first term, plus 5 times the number of fives, which in this case is 5. That's going to tell me what my sixth term is worth, which if we do the math there, that's 25 plus 3. That's going to give us 28. Now, indicate a couple things here. Why is not showing my... Let me change colors. Can I do it over here? Okay, guess not. This is my first term right here. And then this right here, this was add 5, okay? Add 5 fives. I'll write it like this. Add 5 fives to get the sixth term, to get the sixth term. Okay, so could I come up with some kind of generalization? So therefore, could I set up a generalization for term 100? Okay, so term 100 will look something like this. I know it's going to be 3, but it's not going to be 100 fives. We notice it was 1 less 5 because it doesn't include the first term. So it's going to be 99 times 5. We're going to add 599 times to determine that. And we can do some quick math to see that that's 3 plus 495. 99 times 5. And we'll add those up to figure out that it is 498. Okay, so we've come up with a general term. So from the patterns, we can develop a formula called the general term. Okay, and that general term, which gives us the value of t to the n, that is general. So I can say n could be 1, 2, 3, a million, 345, doesn't matter. I can choose any term in this arithmetic sequence, and that is being given to us by the position of that term, n. Okay, so here's what will be provided to you with tests. This is our general term for an arithmetic sequence. So Tn is equal to the first term, T1, plus in brackets, n minus 1, the number of terms, subtract 1, times the common difference, which is what we saw up above. So let's try this out in this question. Okay, so a person is paid $12 for the first hour of work, $19 for 2 hours of work, 26 for 3 hours of work, and so on. So it's nice to work. So we have 12, our next term is 19, and our following term is 26. This is what's happening each term by term. And it looks like it's going up by plus 7 each time. So what information do we have? We know our D, our common difference, is 7. And we know our first term, our term 1, it looks like for the very first hour of work, was equal to $12. So now that we know that, we can find T 15th. I can find the 15th term. So therefore, N is equal to 15 because we're being told that right here, T to the N. So we can take our formula, let's just rewrite it first in its general form. T to the N is equal to T1, the first term, plus N minus 1 times D, the common difference. Okay, so let's plug in some values. So we want to find T15, the 15th term. T1 is 12. And we're going to be using 15 minus 1 this time times the common difference of 7. So we'll just do a couple steps of BEDMAS here. Brackets first, we're going to get 14 times 7. That's going to give us 12 plus 98. Add those up and we're going to get 110. So what does this actually mean? We can say that, therefore, person, because we don't know who this is, person is paid, it looks like $110 for 15 hours of work. Okay, so it looks like the person gets $12 for the first hour, and then they're being paid $7 per hour. Okay, next it says find a simplified formula and just AKA a general term that will allow you to find the pay for any number of hours. And so this case, all we're using now is the TN formula. So again, let's write out our formula first and fill in what we know. And so we got T, the first term, plus N minus 1 times the common difference. Well, recall, we know the first term and we know D. So we're going to plug those in. Our first term was $12. Now we still don't know what N is because this is for the general term, and D is equal to 7. And so we just need to simplify this. See if my color is changing. Nope, it's not working right now. Let's actually move out of this mode. Yeah, let's do that so that I can actually choose different colors here. There we go. Okay, sorry about that. Where were we? So we're just going to multiply this 7 in. We're going to multiply it here and here. So let's multiply by the first term, which is n. So we're going to get 12 plus 7n. And then the second multiplication, 7 times -1 is -7. These, of course, are like terms. We're going to combine them. 12 subtract the 7 is going to give me 5 plus 7n is my general formula. So I would accept this, but we generally put the variable term first. So we could say or t of n, uh, the nth term is equal to 7n plus 5. There's our general. Now, how many hours of work would yield $187? Okay, so now what we need to do is it's asking for how many hours, which was n, is going to yield $187. Okay, so in other words, what's n? We need to determine what n is. So we're going to use our formula from B. So we're going to use formula from part B. So let's rewrite that formula that we just determined, that Tn is equal to 5 plus 7n, doesn't matter which way we use it. And T of n we're being told is $187. And now we just have to solve for n to determine the number of hours. So we're first going to subtract 5 on both sides. That's going to give us 182 is equal to 7n because those have canceled. Divide both sides by 7. And I'm going to have to put that over here. Sevens will cancel, so n is going to equal 182 divided by 7 is 26 hours. There we go. All right, one last question. We have the growth of a particular ant colony produces an arithmetic sequence in which the number of ants is increasing by about 80 ants each month. Okay, if there are 40 ants at the end of the first month, how many months will it take for the ant population to reach 3,000? So let's get a bit of a pattern to look at. It's starting at 40 ants in the first month, okay? And then it's increasing, it looks like by about 80, it says. So we're going to add 80 to that. So we're going to go plus 80. And that's going to give us a new population of about 120, it said. And let's add another 80 to see the pattern in the first 3 terms, first 3 months, I should say. And we're going to get 200 and so on. So we need to figure out, if we keep going and going, when are we going to approximately have 3,000 ants? What is this nth month? Okay, so what do we know? We know our D, our common difference here, is 80. We know our T1 is 40. Okay, we know the Tn that we're trying to determine is 3,000. So that's everything that we know so far. So what we first have to do is let's set up our general Arithmetic sequence formula. This is the equation given to you. You will have, again, this on the test. So the nth term is equal to t1, the first term, plus n minus 1 times the common difference. So what do we know? Well, we want to know at 3,000 is the population. T1 we know is 40. We are trying to figure out n, in other words, how many months, and the common difference is 80. So we do the exact same thing we did before. Sorry, this program is delaying quite a bit. There we go. We're going to multiply the 80 times the n. And so let's rewrite this out. We have 3,000 is equal to 40 plus 80 n. And then the second multiplication is negative 80, negative 1 times 80. Let's combine those like terms. 40 minus 80 is going to give me 3,000 is equal to 80n minus 40. And now we're going to solve for n. So we're going to add 40 to both sides. That's going to cancel. We're going to be left with 80 times n is equal to 3,040. And finally, we're going to divide by 80 on both sides. That's going to tell us that n is equal to 38. So therefore, uh, n is equal to 38 months. Since we have context, we should give our answer in context. After about 38 months, we're going to have a population of 3,000 ants approximately. That concludes our final lesson on arithmetic sequences. Again, this formula will be given to you, but you do need to know what all of these letters and numbers and subscripts mean. This portion will not be given to you telling you what T and T1, N, and D stand for. You do need to understand the equation. All right, we'll see you in class. Have a good one.